Question number 1 says, calculate the volume occupied by 2.5 moles of an ideal gas at STP. STP, what does STP stand for? Standard temperature and pressure. And does anybody know the conditions at STP? 1 atmosphere, so our pressure is 1 atmosphere. Temperature, right? So what's our temperature? 273 Kelvin or 0 degrees Celsius. Not a big fan of the degrees Celsius, but if you don't remember that, on the section that says gases and all that, it's right down here. I think it's the third from the bottom. Remember when you were told that you had to memorize that? All right. Also, does anybody, well, for 1 mole of a gas, and it doesn't matter which gas, whether it's light hydrogen or super heavy radon, okay, these conditions apply. Does anybody know the volume of that gas at STP? Yeah, good. Now, that unfortunately is not on the equation sheet, okay? However, if you remember 1 mole, which isn't on the equation sheet, and these other 2 conditions which are, you can always find that by using R. I won't show you how to do that, but just rearrange the variables and solve for B. Okay, so if we know these are the conditions, that's cool. If not, then we can always do it the old-fashioned way. So the question said, calculate the volume occupied by 2.5 moles. So we'll use PV equals nRT. And the question's looking for what again? The volume. So we want to isolate volume by moving P over. So now we have this equation. And then we can plug in what we know. We have 2.5 moles. The only R that we'll ever use in this class is the atmosphere liter per mole Kelvin. Notice that I put the mole Kelvin on the opposite side of the 0.0821. And I'll do that all the time. And if you want to do that, that's fine. If not, that's fine. Just as long as you're showing me your units. We will use the Kelvin. And the pressure at STP is 1 atmosphere. Okay. So when we cancel out our units, atmosphere, mole, and Kelvin, what are we left with? Liters, very good. And that's our volume. So that all equals, anybody have a number for that? What is it? 56.03, okay. And liters, okay? Now, some of you, I understand, are creatures of habit and want to use PV equals nRT every time. And that's good, there's nothing wrong with that. However, if you're capable of remembering this information here, you may, if you choose, do this. Start off with your 2.5 moles. And if I know the conditions are at STP, what can I put down here? 1 mole. And what goes on top? 22.4. And again, this is a dimensional analysis conversion for conditions at STP, and only for gases at STP. So if it's not at STP, don't even dream of using this. Bad news, it equals the same thing. Okay. So again, this way you can use it for every type of gas problem. This is only at STP. Number 2, it says the density of a gas was measured at 4.97 atmospheres, 96.2 degrees Celsius, and found to be 0.873 grams per liter. Calculate the molar mass of this gas. All right, looking at your equation sheet, there's a couple equations on here that I want to point out for this type of problem. Okay, the first one, and they're all in the gas, liquid, and solution section. The first one, since it gave us a density, is the density, which is about halfway down, not quite halfway, but it's on there. So we have the density equation. We have the PV equals nRT equation, and then we have this equation. So we have these three that are kind of neat. Obviously, we know what density is. It's mass over volume. Okay? We've been using PV equals nRT, but this one, what is that? What does the N represent? Moles. Okay. What does the little m represent? Molality if we're using solutions, but for this side of the sheet, look on your equation sheet. Find a little m on the right-hand side. It's the variable designation. Mass, very good. So the little m in this case represents mass. It will represent molality later on when we work with solutions like freezing point depression, boiling point elevation, all that fun stuff. What's the unit for mass? Grams, very good. Okay. What's big M? Don't say molarity. Not molality. Molar mass, very good. Okay. It's molar mass when we talk about gases. So that's one reason why I want you, if you see that, you're like, oh yeah, here it is. Okay. What's the units for molar mass? What is it? Grams per mole? Good. Okay, so grams per mole is molar mass. So let me see if this works out right. If I take N and I take grams over grams per mole. Now, I'm already very uncomfortable. I don't like having two division lines. Where's mole at in relation to gram? Is it on the same side of the division line or opposite? Opposite. So a much better way to write this, if moles is on the opposite side of this grams, put it there. Okay? What happens to unit grams? They go away and you're back with moles. Okay? So when you look at these letters here, they're really giving you moles. Okay? I don't know, did you guys use this in general chem? No. Okay, that's fine. All right. So, what information do we have? It wants to find the molar mass. All right, so we'll start off with our equation, PV equals nRT. And then we're going to substitute for little m over big M. And what's the question asking for here? What are we looking for? Molar mass, which is big M. So I need to have big M in the numerator, or on top. And since there's no way I can get it on top on the right side of the equal sign, we need to move it. Boom. So now I've got this equation. I need to get molar mass all by itself. So now take PV and slide it over. Now what I have is molar mass is equal to the mass times the ideal gas constant R times temperature divided by pressure and volume. Whew. That's messy. However, we were not given a mass or a volume in this problem. What were we given? A density. So an even cleaner way to set this up is let's have V and P just trade places. Okay? So I'm going to put V right below it and then put P over here on the right. Leave the R and the T alone. So now I've got M over V, which is density. That makes them a little more comfortable. If we want to make them happy, let's put them in their own room. Yeah. Now we're going to get results, all right? So we've got our density, we've got our pressure, and our temperature. We're almost home, guys. Plug it in. All right, so we were given our density is 0.873, and that's grams per liter. So again, put the liter down there. Put it on opposite sides. Now, what this is saying is I have 0.873 grams for each liter of gas. Sounds kind of odd to measure gas in liters, but it's okay. It's still a volume. Okay? And then R, well, R is R. I'm going to slide you over so you're in the camera. Temperature, we said, what is it? Ooh, we gotta change that. 96.2, what is it? 369? Thank you. 369.2, that's a Kelvin. That's ugly. And the pressure is 4.97. All right. So let's cancel out. Oh, I didn't put mole Kelvin down here. My bad. Didn't finish my R. All right, so let's cancel out alike terms. So kelvins go away. Atmospheres go away. Who else? Liters, there you go. So what unit remains here? Grams per mole, which is molar mass. Okay. So we have our grams per mole and whatever the calculator is going to give us there. Anybody get a number? 5.32? I like that. Okay. So 5.32. And the key here is, even though it seems like a long process, it is at times, but after you work with this enough, you'll probably remember that. But the key is, always try to go back to what the units are, or how the variable alignment is. And it's okay to switch places. We're not changing anything by switching the P and the V to make it VP instead of PV. Number 3. HCl can be prepared. So what side of the equation should that be on? The right side. Yeah, if it's prepared, we're going to put it over here. Is prepared by reacting sodium chloride with sulfuric acid. So sodium. You got it right. Sulfuric acid. What mass of sodium chloride is required to prepare enough hydrochloric to fill a 340 milliliter cylinder at a pressure of 151 atmospheres at a temperature of 20 degrees? Okay. Now that's all the information that was given on the question. Does this look like a complete equation? No. So what kind of reaction do we have here? Double replacement. So we've already got our hydrogen with the chlorine, so we also need, good, sodium sulfate. Okay. What kind of problem do we have here? Stoichiometry. Very good. So step 1 for stoichiometry is write a balanced equation. Is that balanced as written? No. So we have 2 hydrogens, so we need a 2 there, 2 sodiums, we need a 2 there. I think we're good. Okay. So step 1, write a balanced equation. Step 2, we need to change what's given into moles. Very good. So do we have enough information here to convert that to moles? No. That's what the question's asking. But here, we're ready. So we get to use PV equals nRT to find out how many moles. So whenever you have a gas problem and it's stoichiometry, I guarantee you're always going to be looking for moles. So to do that, we need to move RT over. So we have PV over RT is equal to N. Okay, so my pressure is good, 151 atmospheres. My volume, what do I need to do to that? Convert it to liters, so 340 milliliters is 0.34 liters. My R, finally, you have an R on the bottom. So 0.0821, and again, this is why I do this. Put the mole Kelvin on the opposite side. It cleans it up. It puts mole and Kelvin where it should belong. And then the temperature, we'll add 273 instead of 298. 293 Kelvin. Okay. Then if we cancel out alike terms, atmospheres go away, liters go away, Kelvin go away, we're left with mole, which is a good number or a good unit that we want. So 151 times 4. So 2.14. Okay. So that is our number of moles. This is step 2. We have 2 more steps. Okay, and this is of our hydrochloric. So what's step 3? Step 1, write a balanced equation. Step 2, change what's given in the moles. Step 3, not yet. Yeah.
Change to sodium chloride.
Okay, so we want to use the mole ratio. Good. So we need to get rid of moles of what we started with, and we need to go to moles of what we're looking for. Okay? So we'll have moles of HCl on the bottom and moles of sodium chloride on the top. Since the question wants to know how many grams we have. And again, the mole amounts are from our balanced equation, so 2 and 2. And let's see here, so are they 2 and 2? Yeah. So it's 2.14. No, I don't think I have enough room. Let me rewrite down here. Make it a little cleaner. Okay, so here what I've done is I've rewritten this so I can show it on the video. What's my last thing that I need to do? Go to grams, very good. So the desired unit for this question is to get it to grams. And the molar mass for that is 58.44? Good. Then we can find our answer from that. So, like 125 grams. Number 4, ammonia is generated by mixing hydrogen gas with nitrogen gas. Ammonia is generated by mixing hydrogen gas with nitrogen gas. Okay? What volume of ammonia can be generated if 30.5 liters of hydrogen at 143 degrees at a pressure of 2.27 atmospheres is mixed with excess nitrogen under the same conditions? Okay. Do we have a stoichiometry problem? Yeah, good. So step 1, we need to write a balanced equation. So we have 3 hydrogens here, 2 there, so let's put 3 here. And 2 there, I think we're good. Okay. All right. Step 2, what do we do? Okay. Sorry. That's right, change what's given in the moles. So, again, if you're given information that's gas related, in other words, pressures, temperatures, all that fun stuff, we need to find the number of moles. So, move that over. Now, do you need to show that every time? Absolutely not. If you can go right from N to PV over RT, you're good to go. The pressure, 2.27 atmospheres. The volume, good, it's in liters, 30.5 liters. My R is on the bottom. So mole Kelvin is on the top. Temperature, it's tricky because it's, for what, 16? Yeah. Cool, thank you. Yeah, don't fall for that trick. Ah, it's in the hundreds, so make sure it's in Kelvin. And anybody get a number for that? 2.3? 2.53. And that's moles. Okay. And I believe you. I'm just going to type this in and confirm. 2.03. That's what you said. Okay. What's the matter? Sounds like somebody's racing out there. Alright, so we have 2.03 moles of hydrogen. Okay, so let's put it here. So step 1, write a balanced equation. Step 2, change what was given into moles. Step 3, we need to use mole ratio. So we'll have moles of hydrogen on the bottom, moles of ammonia on top. And it looks like a 3 for the hydrogen and a 2 for the ammonia. Okay. Now what do we do? Grams. Now, the question doesn't say, or does it? Doesn't come out and say it. But unless it gives you a temperature and a pressure for the ammonia, assume it to be the same. Okay? So since we're looking for a volume here, we need to go back into PV equals nRT. So we need to find out how many moles we have here. So times 2 divided by 3. So 1.35 moles of ammonia. Okay. Now we know our N, we know our T, and we know our P. And we're looking for V, right? How'd I put what? Okay. So PV equals nRT. We need to rearrange it so we isolate for volume. So move P over. So now I've got V equals nRT over P. We're almost home, guys. I'll pull up a chair for this one. So my moles is 1.35. My R is, well, it's R. Got mole Kelvin on the opposite side. Temperature is still 416. And pressure, 2.27. Okay, and I'll admit, this question probably wasn't worded as well as it should have been. But if you don't have any information, the only way we can find volume is by putting it into PV equals nRT. Anybody get a value for this? 20. Okay. So 20.3. Yay, nay?